Hey, this is Blattom, and I'm going to be talking about some game theory. And last time I said that it was the last theory video. I lied. Um, this is the last theory video. This is theory 8. And last time we talked about the indifference principle. So today we're going to do an example where we calculate the Nash equilibrium of a game using the indifference principle. And this is why the indifference principle is so important. Last time, unfortunately, I kind of mangled the statement of the indifference principle. I forgot two very important words, and hopefully it was still clear because, I thought I'd written those words, and the rest of everything was consistent with me having written those two words, but I forgot them. So I'm going to restate the indifference principle. So the indifference principle is as follows. Suppose S naught, Z naught is a Nash equilibrium. So Nash equilibrium, remember, is a pair of strategies. This is your strategy, this is your opponent's strategy, and they maximally exploit each other. And S naught is a mixed strategy, and it mixes pure strategies, and we're going to call those pure strategies S1, S2, ... Sn. So for example, this would be rock, paper, and scissors. And the conclusion is that S1, S2, ... Sn all have the same EV. So these two words, the same, or the two words that I forgot last time, and it changes the meaning quite a bit if you just read it. So S1, S2, Sn, all the pure strategies mixing between all have the same EV versus Z naught. And this is the indifference principle. Also, when I boxed it last time, I forgot the last line, which of course is the statement. So quite a mistake on my part. I'm sorry. I hope no one was confused. But this is the indifference principle. That if you've got a Nash equilibrium S naught Z naught, and your strategy is mixed at equilibrium, and you're mixing between these pure strategies, then all your pure strategies have the same expected value against their strategy, whatever it is. And we gave a proof last time. So now we're going to do an example where we calculate the expected value, or calculate the Nash equilibrium of something using this indifference principle. So I'm going to talk about the game even and odds, or odds and evens. So it's a game between two players. I'm going to call the players Evan and Oliver. Both of them choose a number. They choose either 1 or 2. Evan wins if the sum of those two numbers is even, and Oliver wins if the sum is odd. Right? You get it? Because Evan starts with an E, and he wins if it's even, which also starts with an E. And similarly for Oliver, and odd. So the idea is, it's kind of like rock, paper, scissors, but with only two options. So for example, if Evan throws 1 and Oliver throws 2, well, 1 plus 2 is 3. 3 is an odd number, so Oliver would win. So you can see that this is identical to this, I mean, you can simplify this a little bit, right? Since they're throwing either 1 or 2, Evan wins if the choice is the same. Oliver wins if the choices are different. So if Evan and Oliver both pick 1, the sum's going to be even, Evan's going to win. If Evan and Oliver both pick 2, the sum's going to be even, and Evan's going to win. And if they choose differently, then Oliver is going to win. So it's identical to this game. Right? This is just another way of stating the winning condition. So now let's figure out what the Nash equilibrium is. So you can pause your video and come up with a guess if you like. So let's use the indifference principle. So let's look at it from, let's set up some notation. Let's say Evan throws 1 with probability P, and Oliver throws 1 with probability Q. So, and of course Evan throws 2 with probability 1 minus P because he has to throw one or the other. So these are sort of general strategies. So now let's look at the EV of Evan throws 1, and let's look at the EV of Evan throws 2. And the difference principle tells us that at equilibrium, these two numbers should be equal. The EV of Evan throws 1 and the EV of Evan throws 2. In other words, Evan should be indifferent between throwing 1 and 2. His EV is the same, so he doesn't care what random.org generates. All right, so what's the EV of Evan throwing 1? Well, when Oliver throws 1, he wins. So it's 1 times Q. And then when Oliver throws 2, then Evan loses. So it's 0 times, and he throws 2 with probability 1 minus Q. Similarly, Evan throws 2. Well, if Oliver throws 1, he loses. So it's 0 times Q plus 1 times 1 minus Q. All right, so the indifference principle says EV of Evan throwing 1 is the same as EV of Evan throwing 2. So the EV of Evan throwing 1 is just Q when you clean this up, and the EV of Evan throwing 2 is 1 minus Q. So we get Q equals 1 minus Q. Oops. And of course, this implies that Q is 1/2, right? 1/2 is the only number that makes these two sides equal. So what we know is that Oliver, at equilibrium, is 50-50 between throwing 1 and 2. And of course, you do the same thing for Oliver. So I'm not going to do it because the computation is exactly the same, but you should do it as an exercise if you're sort of hazy about these things. But you find that P is also 1/2. What you do is you say EV of Oliver throws 1 should be equal to the EV of Oliver throwing 2. And the EV of Oliver throwing 1 is going to be 1 minus P, and the EV of Oliver throwing 2 is going to be P. And so P equals 1 minus P, P is 1/2. And so that's the Nash equilibrium, right? So the Nash equilibrium is both players are 50-50. Both players throw each 1 and 2 with probability 1/2.